Where did he go?
I'm recording for him. He's going to the washroom.
Okay. Okay. So, we've already covered everything you guys need for your objectives and your summary. Obviously, don't reference anything. Nobody's done that. We're good. Make sure you have your name, your student number, group number, remember names and date. If you put the wrong group number, there is quite a potential that another TA will pick it up and put it in their pile of labs, and it will be lost for like a month or two until like I can find that TA and be like,
what's our group number?
It's 5.
L05B.
L5B.
Yeah, L5. It doesn't matter as long as the 5 is the thing that's important. Because if you put like a 1, then like it goes to like somebody who kind of like just disappears every day except for the labs, and I don't see them. I think she actually lives in Toronto, and then it gets a pain in the ass for me to actually get the labs back to you guys. So just make sure that you write the right group number, because that sucks for me to try and find it, and it sucks for you guys if you don't get your labs back on time. All right, so first off, make sure that for your results you indicate the right Rockwell scale. So can somebody please tell me what Rockwell scale we use? Okay, perfect. All right, so you have to do a cooling rate calculation. The cooling rate calculation is on the board over here. I'm just changing the lab date while I'm over here. So that's so your your cooling rate is equal to the temperature in the room minus the temperature of that's supposed to be furnace, I don't know what it is, divided by the time that it took to cool. Okay, so it's pretty simple cooling calculation. You're starting at 1050 in the oven there, and you're cooling it down to approximately room temperature, what you determine to be room temperature, or for that matter, what you determine to be the temperature of your sample when you take the measurements is your prerogative, okay? You can kind of guesstimate. I'm not gonna be a big stickler for that. You also have to, when you quench your, or when you take your sample out of the furnace there, you have to start a timer and wait until the sample is cooled, then you stop your timer and you need to record that time, okay? Does everybody understand?
Yo, can you move, man?
So,
Thank you.
anyways,
What is the WQ
so I'm getting there. Okay, so that's how you do your air cooling rate. You have to take the delta and the temperature, and then you take the cooling time. It should be approximately somewhere around 17 minutes likely, but that's what you guys will find out, okay? Relatively straightforward. Your cooling rate should be negative. If it's positive, I'm gonna ask why you guys were heating a sample, okay? Now, for the water quenching, so WQ, that is your water quenching cooling rate, okay? So I'm just gonna give it to you. It's 100 degrees Celsius, negative 100 degrees Celsius per second. I believe it's also in your lab manual somewhere, potentially, maybe not. Yeah, all right. Anyway, so the cooling rate's 100 degrees Celsius per second. You can use that for plotting your cooling curve. Getting to cooling curves, cooling curve. These are cooling curves. I posted on See Learn that you guys all should be bringing these to class. They're very, very important for this lab. So, on each of these cooling curves, you have to draw 2 of your own curves. I want you to draw them directly onto the graph, okay? And then you need to attach these 2 graphs to the back of your lab report and hand them in, okay? So that's 2 curves per graph, 4 curves drawn total. Is that clear? Okay. This is really annoying. Okay, so the first one is your 1045 cooling curve, okay? So you draw one for your air-cooled and one for your water quenched, okay? So that's gonna be a 100 degrees Celsius slope, and then a, whatever you get, it's gonna be like 1 degree Celsius or something like that, slope for the other one. Okay.
What's the room temperature?
I already said that it's what you determine it to be, based on your assumption. Okay.
Okay.
So.
Is it logarithmic?
Yes, so that's the next thing I'm getting to. The scale on the bottom is logarithmic, so even though this is a linear function, you're going to get a curved line because one scale is logarithmic and the other scale is linear. All right? So, important things to note on that are, a logarithmic scale does not start at 0 seconds. A logarithmic scale starts at 1 second. So, for your water quench sample, which starts at a temperature of 1050, what is the first value that you're going to mark down in your graph going to be if the scale starts at 1 second?
950.
950, exactly. So make sure that you understand that. I don't want to see anybody marking down 1050 as the starting point. It's 950 because after 1 second you decreased in temperature by 100 degrees Celsius, which means that you're at 950. All right? So then you're basically going to plot your lines as you go. Put a couple dots in, then you can draw a line, connect the function, and once you have the cooling function, you notice how I'm saying function because this is not experimental data, this is a function.
So you can connect the dots.
So you can connect the dots, thank you, function. You're able to determine approximately what your cooling rate is, and then from that you're able to determine what your microstructural phases are, okay? So, as far as your microstructural phases and the use of a CCT diagram are concerned, what happens is you have different zones on the graph. So you have A, B, F, P, and M. It's all written below what those phases mean, but A means austenite, F means ferrite, P means pearlite, B means bayanite, and M means martensite, okay? There's also MS, just ignore that. Don't even actually know 100% what that means or why it's there. I believe it may be the transition line between martensite and austenite. You should also notice that there is a tiny little start of a dotted line kind of in the martensite region. That is where the martensite region ends, okay?
Yeah.
So, past that line that you could continue to draw down, there is no martensite. All right? So I don't want to get like 15 emails asking, why is there always martensite for this for 1045? You see, so go to your 1045 graph.
Just a straight line, or do we follow a curve?
It goes straight down, yeah. It doesn't matter. You'll notice it will not matter. So you see that little dotted line there? Everybody sees it? Yeah? Okay, awesome. So, you see the curves that are already kind of drawn on the graph. They have cooling rates associated with them. So, let's go with, I'm going to go with, like, say, 42.5 degrees per second, okay? So that's a little shy of the bayanite zone. So it crosses through austenite and it crosses through martensite. But, does everybody remember how martensite is formed? Can somebody give me an explanation of how martensite is formed, please?
What happened?
What is martensite formed from? Like, why does martensite occur?
No.
Austenite shouldn't be there if martensite is formed.
Okay, so I'm going to take it from the top because I feel like you guys, all right, and then I'm going to make you guys all explain it back to me because I don't think you guys understand this. This is really important. All right, so you have ferrite and pearlite, right? Ferrite and pearlite are BCCs, okay? Well, ferrite is a combination of, pearlite's a combination of ferrite and cementite, which are both BCCs. Anyway, point is they're BCCs, okay? Everybody knows what a BCC is on the crystal lattice, microstructures, all that fun joy, right? Okay, perfect, awesome. So, these BCCs heat up, right? Lots of activity, everything starts to expand away from each other. All those atoms start to restructure. They restructure into something called an FCC. That's a face-centered cubic. You guys should know this by now, I hope. Okay, so that's what you call austenite. It's kind of like a semi-liquidous phase, so it's like it's very loose. It's kind of everybody's just kind of chilling, vibrating around, but everybody's really far apart. Okay. Anyway, so what ends up happening is you're able to fit a full atom in the middle. Okay, usually that's your carbon atom. So what happens is it's much more expanded. All right. So then what happens is all of a sudden everybody's up at like say 1,000 degrees. Everybody's chilling, vibrating around, lots and lots of room. And all of a sudden some asshole comes and cools it down really, really quickly, right? And they throw it in water and it cools down rapidly, right? So all these atoms that are kind of chilling out here, all of a sudden they're forced together like this, like go, right? But that central atom, that carbon atom, is not able to escape, okay? So it's not able to escape, so it gets trapped in there. And it's super, super stressed, and it's in a super, super tense structure, and everything starts to restructure around it really quickly, and that creates something called a body-centered tetragon, okay? So there's a highly stressed microstructure, that's your body center tetragonal, which forms something called martensite. Okay? That's what forms when you water quench something. Alright? So the trick to this is austenite is not stable at room temperature. So regardless whether you cool it slowly or you cool it rapidly, it will not be present. Whether it forms a BCC or a BCT, it doesn't matter, it's still not going to be present. Okay? So regardless if your cooling curve passes through the austenite region, what will you not have in your microstructure at room temperature?
Austenite.
Perfect. All right. So, just for recapping, what does an FCC turn into when it is air-cooled?
BCC.
Okay, you guys stop talking. I want people over here. All right, I'm going to point to somebody. Okay, what does an FCC turn into when it's air-cooled? You. Perfect. All right.
Oh wait, you said BCC turning to FCC, not the other way around.
No, BCC is heated up to an FCC, but when it's air-cooled,
Oh, I didn't hear
it
that.
turns into a BCC. Yeah. Okay, so when an FCC is water quenched, what does it turn into? You? Yes, which is also known as, in this case for steels,
Martensite.
it's like writing a cooling graph. If you look at your cooling graph,
Is it Martens? I don't know.
Is the B one?
no, it's more to the left.
A.
No, but what is not present at room temperature? We already went through this. It's austenite. So it would be martensite. Okay.
Martens.
So sorry, I'm
What's this
stressing
M-
this.
M-
It's that like people have discovered that apparently people don't learn what martensite is in this course, and then they get to fourth year where it's really important you understand what that is, and you have no idea what it is, and everybody's confused, and the professors are upset. So I'm trying to help you guys out. This is really important. So
It's only if it's water quenched, but if it's oil quenched.
oil quench as well. It's as long as the cooling rate that is associated with it. It's how rapidly it's cooled.
So they expanded like when when it's heated, that's the austenite.
Yeah, so that's austenite. It's a semi-liquidous phase, right? And it's in an FCC, right? So it's all expanded. Everything's got a lot more room, so you're able to fit a full carbon atom in there, right? Anyways, and then all of a sudden everything just crushes together, and then you get a BCT, super stressed, everything's crammed in together.
So everything eventually turns into martensite, or is that little dashed line where it stops?
That dash line is where it stops, 41045.
Only for
41045. All right. So, we'll get to these. So that's for 1045. Now we go to H13. So, H13 is an iron-based alloy still, so it's a steel. It still has carbon in it, so it still has that conversion from your BCC to your FCC and back down to your BCT and your BCC. The difference is there are alloying agents which work together to alter the microstructure of this alloy. Okay, so the main alloying agents are vanadium, chromium, molybdenum, silicone, and there's a little bit of manganese.
In H13.
H13, yeah. All the properties are written up on the board there. So, the thing about these alloying agents is that they create something called carbides. Okay? Now, carbides are extremely hard, and they give a residual strength to an alloy. Okay? The other thing is that they operate differently when in the presence of carbon and in the presence of heat and cooling. Okay? So, when you look at your H13 graph, you see that there's a whole bunch of different phases that you're not familiar with. So, A is still austenite, P is still pearlite, B is still bayanite, and M is still martensite. The difference is C is vanadium carbide. Okay? And your other section, that's your hash section, that is your precipitation of carbides. So that is a precipitate which is actually formed, which basically is formed from a formation of chromium and manganese and molybdenum, etc., okay? So I don't expect you to know all the alloying agents, just as long as you understand there's a precipitate of carbides that form from the alloying agents separate of vanadium. Now vanadium is a little interesting in that vanadium carbides do not actually solutionize at any temperature. So they don't dissolve. So they're always present. No matter how hot you heat it up, vanadium carbide is always present. Does that make sense? So, if vanadium carbide is always present, that means that there's a certain level of net hardness that cannot be changed or affected by temperature change. Make sense? Because it's always present, okay? So, the other thing is that as you have that austenite, which breaks down into the martensite, okay, so you get martensite that's formed, right? Because it's the rapid transformation. But if you cool it slower and you have time for that carbon atoms to escape from that, they roam around and they're trying to reform those BCCs, okay? What ends up happening is a lot of those carbon atoms are actually picked up by other alloying agents and they form carbides instead of forming ferrite and pearlite. Does that make sense? Okay, so
Say that again.
So that's what you call it vanadium carbide.
vanadium carbide, yeah, so it doesn't, it's a vanadium and a carbon, so it's vanadium carbide.
So is that like carbides that form from like the alloying elements?
Yeah, so vanadium is one of the alloying elements, right?
Oh,
Okay, sorry, you had a question?
No.
Okay, so then you have your precipitates of carbides, which is the other carbides which are formed by the other alloying agents. So vanadium, I include vanadium separately to the other because it is always there. It doesn't dissolve, right? But as you slowly cool it, right, you have that carbon diffusion that happens. You have the carbon atoms that start roaming around trying to reform that BCC. Before they get a chance to form those BCCs in the Fe3C and the cementite, etc., they're picked up by they're picked up by other alloying agents such as manganese, molybdenum, silicone. Yeah, those are the major ones. Anyways, so they're picked up by those. Manganese and molybdenum are really the big ones, and they form other carbides, okay, which are very, very hard.
So it's not called a carbide, it is FeC, like if it's...
It could be, so another word for cementite is iron carbide.
Okay.
But cementite, they're all carbides. Anything that has carbon in it is a carbide.
But the other ones will separate when you heat it up.
Yeah, so everything except for vanadium carbide separates because it dissolves and it separates. Does that make sense? But vanadium carbide's a little special. So as you start to cool this alloy slower, you have these carbides which are forming, and you don't necessarily have that really weak ferrite which forms. You also still will have a presence of martensite due to the action caused by the vanadium, but that's a little bit more complex. So basically, in effect, no matter how quickly or slowly you cool it, due to an addition of carbide formation and the non-dissolution, I think that's the best way to say it, of vanadium carbide, you will have a net hardness that is kind of like a baseline for H13. Does that make sense?
A net hardness.
Yeah, so it's like as your martensite's breaking down, it's decreasing your hardness. You have a formation of your alloying carbides, which increases your hardness, so the net effect is a zero change or a minimal change in hardness. Does that make sense?
Minimal change.
Okay, so similar to your 1045 graph, for your H13, you're going to draw your cooling curves on it. Make sure you plot them, make sure you label them, make sure it's clear which is which, and then you're going to see what area it goes through, and then you declare that as a component of your microstructure. I want you to write all the components of your microstructure in, I believe it's table 2 in your template, if I had a guess. Make sure that you label them for each condition. So that's your water quenched, your air cooled for both 1045 and H13. Does everybody think they have a good understanding of the microstructures of both 1045 and H13 and what occurs based on the cooling rate? Yeah? Does anybody have any questions?
I just trying to understand when you're on this graph,
Yeah.
the B after the martensite end, do these just be continuous and the P continuous?
Yeah, so B is only in this section.
What's over here?
It's blank. It's just blank. Yeah. That blank space, just ignore the blank space. Make sense?
Yeah.
here, and is everything beyond here, and then after this line? it's
Yes,
nothing?
exactly.
So if it's like A, F, P in the line, you figure out. is that-
So if the line crosses through A, F, and P, then it has ferrite and it has perlite, right? Make sense?
The ferrite doesn't turn into perlite?
So ferrite, there's going to be a balance of ferrite and perlite. If you remember from the first lab,
yeah, this
depending on the
is-
carbon content, you have the formation of ferrite and perlite based on the formation of Fe3C, which causes the striation.
Cool. So this table is just listing all of the phases that line goes through depending on water fluid.
Yes, but you need to understand that you're talking about the microstructural phases at room temperature. Therefore, you will not have austenite forming because austenite is not stable at room temperature.
True.
So-
you don't even mention it.
No, because that's what is present in the microstructure at room temperature. Yeah, just the final product.
And for the H13, we list
Everything that's there except for austenite, because again, austenite's not stable at room temperature. All right, so now I'm going to kind of cover what happens when you start to temper the martensite from not a microstructural point of view, but a grain structure point of view, okay? So this is what martensite looks like. I'll hand it around. Everybody can kind of see so they know what I'm talking about before we go to hand this around. So as you can see, martensite forms in tiny little, very, very thin grains that are very, very pointy, okay? Now, from what you guys have learned from previous labs, you should understand that an increase in grain boundaries means an increase in tensile strength. And the constant interlocking means that your dislocations won't go very far, which means that you have higher strength of your material. The problem is that, as you guys should kind of already know, the increase in those points as well as the interaction of those grain boundaries is actually going to decrease your toughness, okay? So it's also going to create stress concentrators at the very point of your martensite grains, which is going to induce what's called a stress concentrator, which will cause crack initiation sites, which will mean that your sample becomes very, very brittle, okay? So if you have something that's just pure martensite, like a piece of metal, if I was holding it here and I dropped it, it'd shatter, okay? Because it's not very tough. It's very, very strong, but it's not very tough. So if I had that sample and I tried to pull it like this, in like an MTS machine, it'd take a very, very long time to break, but when it broke, it'd just shatter, like catastrophic failure-wise, right? And if I dropped it on the ground, it might cause it to shatter, right? Does that make sense? Okay. So we don't necessarily want that, so we temper it. So as I said, we heat it up to a different temperature. As you increase that temperature, you get more carbon diffusion that happens, so you get your 300 degrees Celsius. You start to get some carbon diffusion. You get a little bit of reformation where that carbon starts to escape. As you go up to 700, you get a lot more carbon diffusion, and you start to get like a whole bunch of breakdown of that martensite. And then if you go even higher than that, it basically just re-austenizes, so it turns back into austenite, and then you're basically erasing everything that you've done. Does that make sense? Okay, so that's the martensite. Pass that around. As you start to temper it, you get a reformation of grain structure, but you still have some martensite that's formed. So you guys can see the reformation of grain structure here, here, and here. But if you look very, very closely, you still have tiny little packs where there is martensite present. So that's a combination of different properties, right? Because you have formation of larger grain boundaries, so you're forming your perlite, you're forming your ferrite, but you still have a little bit of martensite. So as I kind of mentioned, the combination of these items decreases the hardness as well as the tensile strength, but it's going to increase your toughness. So it's going to be more ductile, less brittle. So something that's tempered, it'll still be hard. It won't be as hard as something that's completely just quenched, but it'll still be hard. When I drop it, it may not shatter. It may not break. It's more resilient to damage. Make sense? Okay. Then when you austenize it, you're basically reversing everything you did with your quenching. Now at this point, once you've austenized something, all that matters is how you cool it, right? The rate at which you cool it at, because you now have that FCC again, 100%. Everything's formed FCC, and then you cool it depending on the cooling rate. That's what will form your microstructure. So it basically just looks like your regular good old 1045 that you guys saw in the first lab. Make sense? Is everybody kind of getting this? Everybody understands what goes on with the microstructure? You? If you guys don't understand, there's a whole bunch of material in the lab manual regarding quenching and tempering. The chapters are all up there. You guys are also welcome to ask me any questions you want, okay? So, you also have to do 2 tables, or does it only say 1? Nope, 2 tables, yeah. So 2 tables. One table is your hardness versus your carbon percentage, and the other is your hardness versus your tempering temperature. Again, please make sure that you understand your dependent and independent axes, okay? It's literally X, Y. It's written in the lab manual in the order of X, Y. You need to write it in the dependent, independent. Does that make sense? Does everybody understand what dependent and independent means? Okay, does anybody not understand? Like, no judgment here. I'm happy to explain it if anybody doesn't understand. Okay, because there are a couple people who made that mistake. All right, as long as everybody understands it, we're good. So, for your carbon percentage, you're getting your carbon percentage from here. So, everybody should kind of already know this. It was covered in ECOR 1010 because everybody attended ECOR 1010 and stayed awake from the whole thing, right? No. All right, so this is really important and something that should be emphasized more. There's an SAE naming convention, okay? Each number in the SAE code means something different, okay? So the first number means the type of steel it is, whether it's a plain carbon steel, meaning that it's just carbon and iron, or if it has something like nickel or other types of elements, maybe some tungsten, depends, okay? Anyway, so that's what the first 2 numbers mean. That has to do with what type of alloying agents other than carbon are present in the microstructure. Now, the last 2 numbers, that is basically what your carbon content is, okay? So for 1020 steel, you have 0.2% carbon. For 1045 steel, you have 0.45% carbon. 1080, 0.8% carbon. Can somebody tell me for, okay, well, it's already written there, never mind. So 3140, still it's the same thing. It's 0.4% carbon, okay? Then for H13, that's not listed because the H13 has a little bit of a different naming convention because it's an alloy, it's a high element alloying agent, so it's 0.38% carbon. You need all these values, that's where you get your carbon content. Now, for your graphs, you should notice that dependent on carbon content at different temperatures, there will be a greater or less increase or decrease in your hardness, depending on carbon content. Does that make sense? So the slope of your line should change depending on carbon content. Is anybody kind of getting what I'm putting down there? So basically, what I'm trying to say is that as you change your carbon content, the decrease in your hardness will be more. Sorry, I'm having trouble with words right now. Will be more or less exaggerated based on the amount of carbon, right? Because the entire process is driven by carbon diffusion, right? So the more carbon you have, the more carbon there is to diffuse. Okay? Does that make sense?
Do you mean rate of change?
Yeah, rate of change, exactly. So at 300 degrees Celsius, all right, you have tempered it at 300 degrees Celsius. A higher carbon content will see a much more exaggerated drop in hardness than something with a lower carbon content because there's more carbon available to diffuse, therefore a larger change. Does that make sense?
So when you heat it up, carbon goes out.
It diffuses into the microstructure. It doesn't go out of the metal. It just diffuses out of the microstructure, right? So you got your BCT and you got that carbon atom that's trapped inside, right? And then as that carbon atom escapes, and then it tries to form a BCC and tries to form your cementite. Yeah, I'll get it in a minute. So the higher the carbon content, the more carbon atoms there are to escape and to diffuse and to move around.
And that makes BCC
Yes. Does that make sense?
not as hard as
BCT. Yes, that's correct. Because it's not as stress intense. Okay. Anyways, I'm gonna pull these out of the furnace real quick.